bottom of this page. Apply the Lagrange theorem for single variable function to this function, which means f is a two-variable function. We fix the first variable and let the second variable change. The second variable is changed from y0 to y0 plus h. y0 plus l. Okay. F is a two-variable function. We fix the first variable to be x0, let y change in this interval. Then we can apply the Lagrange mean value theorem, because our assumption is that the partial derivative of f with respect to x and with respect to y exists in the whole disk. In this picture, whole disk. Here we only consider on the rectangle, okay, contained in the disk. Therefore, this function as a function of y is differentiable. Okay, on this interval. So we can apply the Lagrange mean value theorem to this function. We will get an c. So this will be the derivative of this function. Derivative of this function is the partial derivative of f with respect to y. So there is a c. There is a c such that the second group of this the right hand side before is the partial derivative of f with respect to y of this function, but the x0 c. Then y0 plus l minus y0 is l. So this part and this the difference of these two terms is equal to this for some c. For some c in y0 and y0 plus l. Okay. Similarly, the first difference here can also be converted to a single variable function. Now the second variable is fixed as y0 plus l, but the first variable changed from x0 to x0 plus k. So by a similar spirit, we can apply the Lagrange mean value theorem to that function. To that function is which is f. The first variable change. The second variable is y0 plus l. Okay. On the interval x0 plus k, apply that to this. We will get plus the differential. The derivative of this function is the partial derivative of f with respect to x. Okay, so this is fx. The x is some eta. The y is y0 plus l. Then the length of the interval is k. Okay, so we get this equality. The difference of f at a plus h and a become some linear combination of the partial derivative with respect to x and y. Okay. Now we use the continuity of fx and fy. using the continuity of fx and fy, it is very hopeful to how to say, okay, and at this point we have not proved the differentiability of f because the coefficient of k and l, there is an xi and eta here. Xi and eta might depend on k and l. Therefore, this is not the differentiability. We need to make the coefficient of k and l independent of k and l. This is the differentiability. But now, the coefficient might depend on k and l. So we have not done. We need to consider more, okay? But by the continuity of the partial derivative which leads back to x and y at the point A, it is hopeful to replace the partial derivative of f which leads back to x and y. That is the coefficient in this final result. It is hopeful to use the continuity at A to replace the coefficient here of k and l to be the partial derivative of f which leads back to x and y at the point A. That is x0, y0. Okay, so I have no space. I need to go to next page. So up to now, we have proved that fa plus h minus fa, that is f x0 plus k y0 plus l minus fx0 y0, which is fx eta y0 plus l k plus fy x0 xi k. This is what we get. Okay, now we use the continuity we just mentioned to rewrite this x0 y0 k plus fy x0 y0 l. Sorry, this is l. Okay, this is l here. Okay, l. Oh, so we have obtained this then, but this is not an equality, right? Because they are obviously not equal, but we can make it to be an equality. How to do this? We need to complement. Okay, so plus fx eta y0 plus l minus fx x0 y0 k plus fy x0 xi minus fy x0 y0 l. Then this is an equality. So now the change of the value of f, has been written in a way by the linear combination of k and l, and the coefficient now is independent of k and l. So it remains to prove that this is the higher order term which leads back to the norm of h. That is because h is kl. So this is k square plus l square. So we only need to prove that the second line of this, the right hand side of this equality, is higher order term. So this is obviously true. Why this is true? Because as h goes to 0, we consider you want to prove that this is of this form. You need to show that divided by this, circled by blue, divided by the square root, divided by the square root, the limit is 0. So since fx eta y0 plus L minus fx x0 y0 and k divided by the square root of k square plus L square. The absolute value of this, obviously is not greater than the absolute value of fx eta y0 plus L minus fx x0 y0. Okay, this is obviously true. But our eta is obtained from applying the Lagrange theorem to this function, to the fixed y let x change in the interval x0 plus k. So the eta here is between x0 and x0 plus k. Okay, the range of eta is in this interval. So since eta is in this interval x0 plus k, as h goes to 0, means that k and L goes to 0. The eta y0 plus L goes to x0 y0. Because both h goes to 0, then k and L are all goes to 0. But eta is between x0 and x0 plus k, so eta goes to x0. Eta goes to x to 0. Therefore, the eta y0 plus L goes to x0 y0. So by the continuity of the partial derivative of f with respect to x, by the continuity of fx, you see that the right hand side goes to 0. The absolute value of the difference of the value of fx at these 2 points goes to 0 when h goes to 0. So this proves that the first term here is of the form here, because divided by the square root, the limit is 0. Okay. Similarly, you can prove that the second term also of this form also is a higher order term. So in conclusion, fa plus h minus fa is a linear combination of k and L plus the norm of h higher order term. Okay. So this proves that f is differentiable at A. Conclude the proof of this theorem. Okay. The next thing we want to talk about is the directional derivatives. So our function f is defined near A. We recall that the partial derivative with respect to xi at the point A is the rate of change. This is the rate of change at A along the EI direction. 0, 0, 0. The ith component is 1. Other components are 0. Okay, but of course, it is natural to replace the EI direction by other direction, more general direction, and consider the change of the value of f along all kinds of direction. So this is E1, this is EI. So A is here. So you not only can consider the change of f in this direction, you can also consider the change of f in other direction. Okay, consider how f varies along this line. Okay, so this is the idea of directional derivatives. So L. So our f is defined in the neighborhood of A, right? Here is A. Our f is defined in this R neighborhood of A. So given L, a vector in Rn, for epsilon small, how small? Our f is defined in the R neighborhood of A. Now, if epsilon is greater than 0 but less than R divided by the norm of L, here we make a convention that if L is 0, then this is infinity. This is our convention. Okay. Then whether L is 0 or not, for any epsilon in this interval, 0 and R over the norm of L, we have a function. The point A plus TL belongs to this neighborhood for all t in the interval minus epsilon, as you can see. Because the TL, by the definition of epsilon, the norm of TL is less than R. Okay, therefore, A plus TL belongs to the R neighborhood of A. So we have, because this point contained in the domain of definition of our function f, so we have a single variable function phi minus epsilon, given by phi t is the value of A plus TL. Okay, we have this function. So if this function, if phi is differentiable at 0, then we defined the directional derivative of f at A in the direction L. Directional derivative of f at A in the direction L to be the derivative of phi at 0, which is t goes to 0, f A plus TL. F A plus TL is phi t minus f A. This is phi 0 divided by t. I'm sorry, I have not enough space to write, therefore I need to write minus fa here. Not very beautiful. Okay, so this is the definition of directional derivative. Okay, this is the sensibility of the previous definition of partial derivative. In the definition of partial derivative, the direction is E1, E2, En, the standard base vector in Rn. But now we can replace the E1, E2, En by arbitrary vector L. Okay, so this is the definition of directional derivative. We also use the notation partial L F A. We also use this notation, but you need to be careful. You don't need to you should not mix this with the partial derivative notation DIFA. So in DIFA, I is 1, 2, 3, n. But in our DLFA, L is a vector, a direction. So you can distinguish these two notations from the context. Okay.